Welcome back to Math 104. What is the probability that a patient whose condition does not improve took the actual drug? Is this a conditional or unconditional probability? This is a conditional probability. We are focusing on patients whose condition does not improve. That means we are restricting attention to the 32 people in our ideal data set of 100 people who do not get better. Among those 32, what fraction took the actual drug? That's 14 over 32. And in particular, this equals the probability of A given, not B. Given that a randomly selected patient does not improve, what is the probability that that person took the actual drug? That's 14 out of 32. At the beginning of the course, we posed several problems that challenged our intuitions. One of them was this one. If 0.5% of the population has a certain disease, a medical test for it is 99% accurate, and your friend tests positive, which is more likely? That your friend does have the disease, or that your friend does not have the disease? If you're like most people, your intuition suggests that in light of the high accuracy of the test, your friend probably does have the disease after testing positive. The trouble with this intuition is that it overlooks the importance of this 0.5% of the population that has the disease. What role does that play? That's what we're going to work out now. Before we do, we have to understand the two ways a test can go wrong. A test result for the disease can be incorrect in either of these two ways. It could be a false positive, which means that the person does not have the disease, but the test result is positive nonetheless, so the test wrongly tells the person you have the disease. The other way of getting it wrong is with a false negative. That is, the person does in fact have the disease, but the test result is negative nonetheless. The test tells the person, oh, don't worry, you don't have this disease. But that would be a mistake, and a terrible mistake, if the person actually does have the disease. Now let's stop and think for a minute. Which is worse? Is it worse to be in the situation where you receive a false positive test result, or is it worse to be in a situation where you receive a false negative result? The false negative is worse because you might need treatment, and you won't even think of getting treatment because the test told you there was nothing to worry about. This is very, very dangerous. Whereas a false positive might scare the heck out of you, but if you go get tested again, you'll have a good chance of finding out that no, actually, you don't have the disease. Let's look now at an example that separates out false positives from false negatives. In a certain city, 0.1% of the population is infected with the Zika virus. That's been in the news lately. A test is administered, and 95% of those who have the Zika virus test positive for the disease. 10% of those who do not have the disease test positive. That would be a false positive. So there are two ways of testing positive for the disease. You could test positive because you do have it, or you could test positive in spite of not having it. Let's draw a tree diagram which represents this situation. We have to start drawing the tree with unconditional information. The unconditional information has to do with who has the disease and who doesn't have the disease. The other information that's given is conditional. This 95% is not 95% of everyone, it's 95% of those who have the virus. This 10% is not 10% of everyone, it's 10% of those who don't have the disease. We first have to separate out those who actually have the disease from those who don't. In our tree, the first branching is therefore between having the Zika virus and not having it. We have to be really careful now about this 0.1%. The probability of having the Zika virus is not 0.1, but rather 0.001. This is 1/10 of 1%. 1% would have been a 0.01 probability. This is a tenth of that. That leaves a 0.999 probability of not having the Zika virus. At the second branching, a person can test either positive or negative. Positive or negative. If someone has the Zika virus, the test has a 95% chance of detecting it. A 95% chance of reporting a positive result. That leaves only a 5% chance of giving a false negative. This negative would be a false negative. This is someone has the disease and nonetheless tests negative. This is very bad news. For those who don't have the disease, there is a 10% chance of testing positive, that's a false positive, and therefore a 90% chance of a true negative. We're ultimately going to want to turn this into an ideal data set and set up a table, but it's actually very helpful to start with the tree in these problems where you're given some unconditional information and some conditional information. What is the probability that a randomly selected resident of the city receives a true positive result? Is this a conditional or unconditional probability? This is an unconditional probability. We can tell it's unconditional because we're asked about a randomly selected resident of the city. That means we're selecting randomly from the entire population. What is the probability that someone selected randomly from the entire population receives a true positive test result? The true positives are right here. This is the event has the virus and tests positive for it. The probability of that event equals 0.001 times 0.95. That's easy to compute because it's 0.00095. Multiplying by 0.001 just has the effect of moving the decimal point 3 places to the left. Thus, it's a small fraction of the population, less than 0.1% of the whole population, that receives a true positive test result, has the disease and tests positive. Let's interpret this situation in terms of an ideal data set of 1 million residents. First, we need the probabilities of each of these 4 events, because they correspond to these 4 entries in the table. We already computed 0.001 times 0.95. This is the probability of a true positive. That was 0.00095. The probability of a false positive is therefore 0.001 times 0.05. That's 0.00005. There are 4 zeros there. The probability of a false positive, the probability that a randomly selected person does not have the virus but tests positive anyway, that equals 0.999 times 0.1, and that equals 0.0999. These have all been very small numbers so far, so the probability in this last category must be quite large, the probability of not having the disease and correctly testing negative for it. That's 0.999 times 0.9, that equals 0.8991. Let's put this together to get our ideal data set. How many people out of 1 million will have the Zika virus and test positive for it? Well, 0.00095 times 1 million, which is 950 people. How about having the Zika virus and testing negative? That's 0.00005 times 1 million, which is 50 people. You don't need a calculator to turn these probabilities into whole numbers here by multiplying by 1 million. Multiplying by 1 million moves the decimal point 6 places to the right. Thus, the number who do not have the Zika virus and test positive, that's 0.0999 times 1 million, which is 99,900. And finally, the overwhelming number of people, those who do not have the virus and they test negative, there are 899,100 of them. Now we can think concretely in terms of these whole numbers of actual people who in total form a population of 1 million. Those who have the virus number 1,000 in total. Those who do not have the virus number 999,000 in total. As for those who test positive, there are 100,850 of them. And how many people test negative total? 899,150. This is a very concrete way of thinking about what's going on and making the comparisons we're going to need to make when we start talking about conditional probabilities. If everyone in the city is tested, what percentage of the population tests positive? In other words, if a resident is selected at random from the entire population, what is the probability of testing positive? We've already done the hard work here. We see that it is 100,850 people out of a total population of 1 million who are testing positive. That's just 0.10085, slightly more than 10%. One of the very helpful things here is that we get to see the breakdown among those who test positive. There are a few who actually have the virus, but there are many who do not. Before going on to the next video, answer the following truly pivotal question. What is the probability that someone who tests positive for the Zika virus actually has the disease? In other words, if your friend tests positive for the disease and is very nervous about what this means, how likely is it that your friend really does have it?